So today we're going to do just a lot of proof writing. We started this last time, and we're going to pick it up today. And we're going to get into more geometric proofs. It's going to be a little bit tough. It's going to be a little bit weird. Your proof writing career is just getting started, and it's going to kind of get real today, right? So we'll fight through it, and we'll figure out how to get going with these things. But bottom line is, at some point, you're going to have to just start writing statements and get past the student freeze up, right? But we'll talk about that when we get there. What we're going to do today is a couple of things. One, we're going to start getting into and practicing how to write proofs, but we're also going to continue to build on the tool chest for proof writing, right? Start putting more rules out there that we can use. We'll talk about some theorems. We'll talk about some more postulates, and then we'll start bringing in a lot of the definitions that we've been putting out there so far. You're going to have to know your definitions and know what they say, okay? So every time we prove a theorem, that gives us a new rule for us to be able to use in a proof. And we'll talk a little bit about how to get that done, okay? All right, so we'll just jump right in, right? The first theorem that we're going to talk about and prove is this one, which is going to sound incredibly obvious, which is the right angle congruence theorem, which says, all right angles are congruent. No joke. But again, having to bounce between the numerical world of geometry versus the figure world of geometry, we should know something about the measure of right angles, but we haven't actually talked about right angles being congruent, the figures themselves being congruent. So we can do that here. Now, any good theorem, any theorem period, whether it's good or not, needs a proof. Theorems are those rules that need to be proven. The postulates are the things that we just kind of accept as being true. So we need a proof of this guy, and so we'll walk through that right now. So let's say we're given two right angles. Angle 1, angle 2 are right angles. We know that right off the bat. So it was given to us, right? We always start our two-column proofs with given information, okay? And then we freeze up for a second, because that's what you do when you start to write proofs on your own and you have no idea where you're supposed to go next, right? So then from here, understand two things. Any statement in a proof has to come from information that you put in the proof before, or can come from a diagram if we have one to work off of, right? So if we could pretend like these statements written down here weren't actually here, I would ask you, well, if you know that angle 1, angle 2 are right angles, then what can you tell me about those? Right, and so that's what you would write down next, right? Because they're right angles, I know that the measure of angle 1 and the measure of angle 2 are both 90 degrees. Now, why? How did you know that? Right? You didn't always know that. You weren't born with that information, right? Something told you that. And the definition of right angle says that if an angle is a right angle, then the measure is 90 degrees. So that's how we're going to use our definitions, right? So again, you have to know your definitions for those vocabulary terms that we've been throwing out there, because we're going to use them. Okay? All right. Then from here, you would have to try to figure out what to write from the previous information. And we've done this sort of tactic before, this method before, but in your algebraic proof it works pretty well. But if the measure of angle 1 equals 90, the measure of angle 2 equals 90, then we can take this 90 out and substitute that for the measure of angle 2, right? And so by substitution, we can write down the fact that the measure of angle 1 equals the measure of angle 2. Okay? And then from here, we're still in the, well, we're not still, but we're in the numerical world of geometry, and we're trying to prove that those two angles themselves would be congruent. So we got to make that jump from the numerical world to the figure world of geometry. And so since we know that the measures are equal, then of course that means that the figures themselves are going to be congruent. And what allows us to make that jump is the definition of congruent angles, right? And we would use the same if they were segments. The definition of congruent segments would make that jump for us also. So we can use this definition to make the jump from measures to figures being congruent, or from figures being congruent to measures being equal. That's how we make that leap between the two. Okay? All right, so now we know that two angles are congruent, right, if they're right angles, which we should have known already. But anyway, next, we'll keep adding here, right? The linear pair postulate, right? If two angles form a linear pair of angles, then they are going to be supplementary, right? That should make sense also, right? If two angles are a linear pair, then we know that they're going to form a straight angle, right? Call this angle 1, angle 2. And of course, if they will form a straight angle, they have to add to 180, and that's where we get the supplementary part, right? Now, this is a postulate. Postulates don't need to be proven. We just accept them as being true, mostly because they make a ton of sense. Okay? Quick side note here. When are angles in a linear pair equal? If they're right angles, right? We talked about that a little bit before. But if they're right angles, then they'll be equal. And they'll be a linear pair, right? I mean, they need to be adjacent in right angles, but in order to be a linear pair, the angles have to be adjacent anyway, right? So there you go. Little side note, right? Next, that helps lead us into another theorem. And the theorems are just like the postulates from before. I don't need you to know the numbers. There's no sense in memorizing the numbers for the theorems. Again, if you get into another textbook, the numbers would change. So those are kind of arbitrary. Just know that this theorem is called the congruent supplements theorem. Basically, what the congruent supplements theorem says is that if you've got two angles that happen to be supplementary to the same angle, they're going to be congruent. Or, if you've got two angles that are supplementary to two congruent angles, then they're going to be congruent, right? There is a quick, fairly nice numerical proof of this. That just takes a second. So I'll show you what happens here. This is basically what it says. Let's say that angle 1 and angle 2 are supplementary, right? And I know the measure of angle 1 is 100 degrees. What's the measure of angle 2 going to be? Yeah, 80. You've got to add to 180, right? Okay. What if we also know that angle 2 and angle 3 are supplementary? Then what's the measure of angle 3 got to be? 100. Now look at angle 1 and angle 3, right? Since these guys were supplementary to the exact same angle, then of course they're going to have the same measure, and then we can say that they're congruent, right? That's what this theorem is saying, which is fairly obvious, right? A little less obvious than that was, okay, what if we reset, and we know that the measure of angle 1 and the measure of angle 2 are supplementary. We also know that the angle 4 and angle 3 are supplementary, right? So we've got, and this is way too short of an abbreviation, but this is for time purposes. So 1 supplements 2, and we've got 3 supplements 4, right? And then as long as we also know that angle 2 and angle 3 are congruent, then we can make a link here too, right? All right, so these guys are supplementary, so we're going to keep the same angle measures here. We know these guys are too, but more importantly, we know that 2 and 3 are congruent. So what's 3 going to be? 80. And since 3 and 4 are supplementary, what's 4 going to be? 100. Now look at 4 and 1. 4 and 1 were supplements to 2 congruent angles, so they're going to be congruent also. This is what this theorem is saying. Okay? So that's kind of a generic numerical way of proving that theorem. A good geometric proof would look something like this, right? So That's what the theorem again says. Angle 1, angle 2 are supplementary, then angle 3 and angle 2 are supplementary, then 1 and 3 are going to be congruent. Okay? A good geometric proof would look something like this. All right. So let's say that we are given the fact that 1 and 2 are supplementary and 3 and 2 are supplementary, right? Again, we're trying to get comfortable with the idea of what to do next. There's the given information. Where do you go from there? We don't have a diagram to work off of, so we look at the statements. What do you know because those angles are supplementary? They add to 180, right? So we can write that. Might as well put it in our proof. Not having any idea if that's going to help us get to where we want to go. We're just going to write it in there anyway, right? And the reason why we get to write it in there is because that's the definition of supplementary angles. Okay? It's also kind of our first glimpse at if two statements are going to use the same reason, you can lump them into one step in a proof. That makes enough sense, right? All right, so we look at this. We've got 1 plus 2 equals 180. 2 plus 3 equals 180. Since both of these sides equal 180, then we can use something to get to here, right? I'm starting to say it, substitution. Yeah, we can substitute them in. We can use substitution to come down here and say that 1 plus 2 equals 3 plus 2, right? It should be a property. We need to make sure to include that it's a property, but substitution property, right? Now that we're here, if I were looking at this equation right here, hopefully we would realize that, hey, we got the same thing on both sides. So maybe I can just subtract that measure from both sides, right? What says that we can subtract the same thing from two sides of an equation and that's okay? It's the subtraction property, right? The subtraction property, right? And then we're going to actually do the subtracting out here and get down to 1 equals 3. What are we doing when we do that? That's your simplify, right? That's why I crossed out substitution. Call it simplify, right? And then, all right, but we're still talking about the numerical world of geometry. And we wanted to prove that those two angles were congruent. So we need to be in the figure world, right? So make that leap. Go from the measures being equal to the angles being congruent by using that definition of congruent angles, right? So there's your proof of that theorem. Now we can use the theorem anytime we have two angles that are supplements to the same one, we can just say they're congruent right off the bat. And we'll use that eventually to see it in action. All right? Just building. We're just building. All right? All right. By the way, this stuff works for complements as well. We have the same theorem for complements as we do for supplements. If two angles are complementary to the same angle, or if two angles are complementary to two congruent angles, then they're going to be congruent. Okay? I can take you through the same numerical exercise that we just did, but it would be the same thing, only instead of 180, they're going to add to 90, and the measures are going to change a little bit. But it'll be the same thing. Right? So again, basically we're trying to say that if angle 4 and angle 5 are complementary, and 6 and 5 are complementary, then 4 and 6 get to be congruent. Okay? And I'll let you get this in and fill this in, but it's going to look a whole lot like the last one did, right? Not anything brand new out of that. Obviously, we start with the given. If we're given that 4 and 5, 6 and 5 are complementary, then we have that in there to start because every proof starts with given information. And then once we know they're complementary, we know they're going to add a 90 because the definition of complementary angles. Then we can use substitution to say 4 plus 5 equals 6 plus 5. Then we can subtract the measure of angle 5 from both sides because that's a common piece out of both sides from the subtraction property. Then we can simplify down to 4 equals 6 and then use the definition of congruent angles to get to the figures being congruent, right? So hopefully it makes enough sense that the proof looks like the same as before. Only take supplementary and 180 out and put complementary and 90 in. Okay? But the moral of the story is we can use this theorem now. It'll shorten our work. If I know that two angles are complements to the same angle, I can just call them congruent and say it's because of this congruent complements theorem. Okay? That's it. Good? All right. Very few things that we get to assume out of a picture. We mentioned that before. These two things are just a couple of those few. Right? Go ahead and take a shot at sketching and labeling vertical angles, and then sketching and labeling linear pair. Right? Being able to recognize them would be very, very useful when we start trying to put together our proofs and some of the theorems that govern these guys. Right? Okay, let's get these in. If you're going to sketch vertical angles, what are you basically going to draw? An X. Right? We talked about that. An X. Right? Vertical angles are created when two lines intersect. Right? And so there you are. And so as long as you are looking at your vertical angles as the ones that are back to back, sort of looking away, right? You probably want to go ahead and write those in as which ones are your vertical angles. And so obviously 4 and 2 are going to be vertical angles, and 1 and 3 are going to be vertical angles. If you can recognize that, then we can start to work on those angles. And we can assume that because even in a computer-generated image, we can tell if these lines are straight lines or not, right? Well, all lines are straight lines. But we can tell if this guy is bending at all or if it really is a straight line, right? Straight line X. So we get to assume that. Linear pair, for the same reason, is something else that we can assume. So your linear pair, all you need to do was create two angles that share a side and form a straight angle. Right? And again, because it forms a straight angle, we can tell if two angles are going to be a linear pair. Right? So 5 and 6 here are going to be a linear pair. Right? We don't have to do anything to establish those guys as being vertical angles or linear pair. We can just say they are. All right? Now that we can recognize vertical angles and linear pair, how can we use that? Well, there is some interesting information about vertical angles. I've mentioned it before. And that is that all vertical angles are congruent. Right? From your vertical angles congruence theorem. And if you're going to use these theorems that we're proving, you need to call them those things. Right? Notice this guy doesn't even have a number next to it. Just when we use this as a reason to say something in our proof, then just say it's because of the vertical angles congruence theorem. You do need to at least memorize the name. If not, you have to write out what the theorem says. And that's no fun. Right? But anyway, vertical angles are congruent. And before we can use it, we really ought to see a proof for it. So here's the proof that sets up. And in that diagram, we're told that angle 5 and angle 7 are vertical angles. But we could tell that already. So obviously in a proof, we're going to start with our given information. Angle 5 and angle 7 are vertical angles. Okay, great. This is where proof writing gets hard, right? What do you write next? Right? Because in a little while, you're going to have to do this by yourself. Perfect sense. So we can come in here and say, all right, 5 and 6, and not just 5 and 6, but actually 6 and 7 too, right, Emma? 6 and 7 are a linear pair also. She has no idea. I don't have any. You guys have no idea if this is going to help us prove that 5 and 7 are congruent. But it's true. Right? That's proof writing. You write it in here, and you hope it helps you get to where you want to go. Right? And we know that. What reason are we going to use? How did you know that 5 and 6 and 6 and 7 were a linear pair? That's true. It was kind of the same thing as the right angles being 90 degrees. We knew that because the definition told us that they were going to be 90 degrees. Okay? Good. A lot of good ideas thrown out there, but we'll try to keep this, it's KISS method, right? Keep it simple. Keep it simple, silly. Right? All right, anyway. Now, Reed and MSR talk about probably where we're going to go next, right? If you know that these guys are a linear pair, then what else do you know about those angles? Yeah, they're going to add up to 180, right? Which means that they're going to be supplementary. Right? If they're a linear pair, then we can go ahead and call these guys supplementary. Right? And that linear pair postulate that we just took a look at said that. And since the linear pair postulate said it, we can use the linear pair postulate here to say it in our proof. All right? Now, okay, that's it. So we can just jump right down and say that 5 and 7 are congruent because of that congruence supplements theorem. That's how we're going to use it, right? Otherwise, without this theorem, we would have had to walk through what we wanted to do before, and that's add these two angles and set them equal to 180 and go through that whole mess, right? But now we don't have to. We can just jump right down and say that these guys are congruent because of the congruent supplements theorem. Okay? Does that make sense? Writing statements from what you know. Hope, beyond hope, that gets you where you want to go. Hey, that rhymed. Okay. Moving on. We've got a few more proofs here that we want to get to, and really it's just more about practice writing proofs. Okay? That is what we just talked about is kind of the nature of writing proofs. You write in your given, you look at your diagram if you have one, you look at your statements that you've written into your proof, and you just start writing what you know because of that stuff. Right? And you'll use what works and you won't use what doesn't. Right? And we got to fight through it. But again, I'll say, the bottom line is you have to start writing statements. Okay? I expect, as we go through proofs together, for your old erasers to be going crazy. You should be erasing stuff and changing stuff all the time. Because you're going to make a bunch of mistakes. And that's okay. Right? So we're going to talk about, there are some statements about segments and angles that we're going to go through and walk through and prove, but it's more about you getting more practice writing proofs. Okay? All right, some quick definition work for you. We've been doing this stuff, but we haven't actually defined the first two, a proof. A proof is a logical argument that shows a statement is true. Lots of different kinds of proofs. We'll focus on two-column proofs. Two-column proofs is just a nice structure. It's a flow. It's a logical order. Being a math guy, my universe is much, much better when everything is in a logical order, when everything makes sense. If it's not logical, I tend to go a little berserk. Okay, and then the definition of a theorem, a statement that not only can be proven, but needs to be proven, right? It's a statement that needs to be proven. Postulates we don't have to worry about, but theorems we do. We'll just go right into it. Here's a proof. Let's go figure out how to write it. Okay? Here we go. We're given that the measure of angle 1 equals the measure of angle 3. And what we want to prove is the measure of angle EBA and the measure of angle DBC are equal. And we're given this diagram over here. Diagrams are helpful. They show location. They show relationships, and that we can maybe use some of them. All right? Two-column proof. Let me get started. We need our statements and our reasons. The very first statement you're always going to put in a two-column proof is? Given. The given. So we're given the measure of angle 1 equals the measure of angle 3 that was given to us. Okay, great. What's the next statement? We look at that picture, and we right off the bat know that 2 and 3 are together, and so we can add those guys together. We're still talking about the measures. Right? And what has told us that we can do that? That's it. That's going to be your reason then, the angle addition postulate. All right, so 2 and 3 add to EBA. Great, by the angle addition postulate. Does that help in our next one, maybe? If we added 2 and 3. Sure. Sure, why not, right? I don't know if this helps, but I know it's true. And I know I can do it by the angle addition postulate. Right? Do that. Yeah, so we can do that. The idea thrown out here was that we're going to add the measure of angle 1 plus the measure of angle 2, and then say the measure of angle 3 plus the measure of angle 2. And that's because of? Yeah, the addition property. Right? So we're able to substitute here. 2 plus 3 to 2 plus 3, so just grab EBA and bring it down here. 1 plus 2, we can bring it down, DBC down here. And, hey, look at that. That's exactly what we wanted to prove. So we're done. Right? So we're done. Good. Nice job. Good work. I think it's deserving of a round of applause. If it still doesn't make sense, that's okay. Okay? It will. I promise. I'm going to go through and try to work our way through this guy right here. Okay? We know, we're told that AC equals AB plus AB. Right? And we want to prove that the length of AB equals the length of BC. So, get your given in there. I'll give you a couple of minutes. Try to write the next statement or two, or if you feel comfortable enough, finish it. And then we'll go through it together. Quick, because you guys are, we're kind of getting all stuck at the same spot. That's okay. All right? So, we get in our given here. Right? So, AC is equal to AB plus AB. That was given. Right? Next. Look at this statement here. I know some of you guys were having a hard time coming up with what to do. We had one that wanted to subtract AB from both sides, use the subtraction property. That's okay. You can do that. Right? I think what you would find is it's not going to get you where you want to go. And I know you don't know that yet, and that's okay. But if you did that, you may end up having to take that step out or realizing that you didn't need to do it. Right? So I keep pointing you guys in the direction of the diagram also. Right? What do you know because of the diagram? What can you write from the diagram? Right? And so Avery?
Segment addition postulate.
Right. We can do the segment addition postulate. And if we use the segment addition postulate, we were going to write what? That AC is equal to?
AB and BC.
Okay. Don't know if that helps, but I know it's true. And just like subtracting AB from both sides, I don't know if it helps, but it would certainly be right and would certainly be true. Right? Okay. Next. We'll look at these first two statements. Every time you write a proof, we've written 3 or 4 proofs in here today. Every time you see some steps that we use, some steps that we write, take those with you as possibilities of doing that again. Right? We've got AC equal to this, and we've got AC equal to that. Right? What have we done in our past proofs when this has happened? Right? Okay, what have we done?
Subtraction, so AC minus AB equals BC.
That would make enough sense. So we're going to take AB plus AB and put it in for AC. And we can do that because of the substitution property. Okay? Already heard it. Right? Say it again. It was over here. Who said that? What were you going to say? Go ahead. Subtract what? What do you want to subtract?
AB from both sides.
Yeah, we've done that before, right? We can do that here. Okay? The subtraction property says that we can subtract the same thing from both sides of an equation. Okay? And watch what happens. This gets you 0. That gets you 0. So you end up with, when you simplify, you get AB equals BC. We're given this diagram, and we're given this information. M is the midpoint of AB, right? Of segment AB. In the last proof, you couldn't assume that that point in the middle was a midpoint because we didn't know it was. You can't assume that, right? But now we're told it is, right? And then you want to prove two things. And it's really pretty easy to see once you get to this guy in A, to get to the B, all you got to do is divide both sides by 2. Use the division property. Does everybody see that? Divide by 2 here, and you're going to get AM equals 1/2 AB. So you're really just proving this guy. Step 6 and step 7 should be these two guys right here. Right? We're proving two things, but we're doing it all in the same two-column proof. All right? So go ahead and try to get in the next couple of statements once we put the given in there, right? I know it's hard. It's going to be tough, but try it. All right, so let's run through this proof really quick. Like I said, we know that M is the midpoint of segment AB that was given to us, right? So what we can go do from here is that tells us that segment AM is congruent to segment MB, right? And we know that because of the definition of midpoint. Right? The definition is what told us that a midpoint creates two congruent segments. All right? But if you notice up here, we're using the measures, not the figures themselves. Right? There's a difference between putting a stick above AM and just writing AM. Right? We need to make that jump over to the numerical world of geometry. And that's what we're going to do here. We know that if the two segments are congruent, then the measures are going to be equal. And what we use to make that jump from the figures over to the measures is that definition of congruent segments. We would use the definition of congruent angles to make that jump for the angles. Okay? All right. So we've got this in. We're still trying to get AB equal to 2AM. What else can we do? And I'm not sure what else to do from this definition of congruent segment statement, but look in your figure, right? We've done this before. Look in your figure and write what you know from the figure, right? And from the figure, we see that we can take AM and add MB to it, and when we do that, that's going to equal the entire segment AB. We've done that before. That's because of the segment addition postulate, right? All right. Something else that we've seen before, and proof writing is always bringing back what you've seen before. If you look now, AM is equal to MB. And NB shows up down here. So that means that we can take AM and substitute it in for MB. That's our next statement. AM plus AM equals AB, and that's because of substitution. All right? Which is helpful because if you look back up to what you're trying to prove, it's an equation that uses AB and AM. And now we have an equation that's all AM and ABs, right? So that's kind of good. Well, sorry about that. Didn't wrapping this up at the end of the school day here. But anyway, now we can take AM and add them together and say that 2AM is what you would get if you added those, would be equal to AB, right? And that's just that's us simplifying, right? When we combine like terms, we're simplifying, so we can use that. Okay? And then we're one more step, right, to get to the part B of our proving. We're one more step. We'll just divide both sides by 2, right, using the division property. And we get AM equals 1/2 AB. Now, we really ought to have an extra step in here so that we had room to show the division in the division property, and then another step to simplify. But just for space purposes, we didn't do that here. So, but there you go. There's your proof of this guy. Again, my last piece of advice as you start to write these proofs on your own, eventually, is use what you've done in the past, use what you've seen in the past, and just be brave and write the next step. Even if it's wrong, we'll fix it. All right? That's it. Homework's out in Canvas. Have it done by next time.